Hello, everyone. Let's start this discussion. Today, we are going to talk about the precision testing for analog to digital converters. And we are going to use IEEE 1057 as the framework for defining this testing methods and the parameters that we wanted to use as a criteria for evaluating the ADC's performance and accuracy. Uh, Today's discussion is basically not just about the standards. We wanted to discuss the different ADC architecture and how they have a different behavior and characteristics. We are going to talk about the testing configuration, and also we are going to discuss the measurement techniques so we could have a reliable and repeatable result uh, in our validation and evaluation. Now, before we start talking about the IEEE 1057, let's ask a more fundamental question. Why do we care about the ADCs, analog digital converters, so much? Basically, let's start from the kind of like a background. DC signals are basically the backbone of a physical measurement in our evaluation, in most of evaluation. What we define as a DC signal is a constant, meaning non-time varying voltage or current, like a battery output or temperature sensor reading or voltage leveling control loop, a static pressure reading. All these considered as a non-time varying or slowly, very slowly, kind of like varying signals. We categorize them as a DC signals. Now, ADC converts these constant analog signals to a digital code. Okay, so we have a boundary of our DC signals. For example, the DC signals would change from 0 to 5 volt. Okay, that could kind of like represent the temperature changing, okay, in the room. And then we are gonna try to code that range of the analog voltage to several digital code. For example, when we have a 3-bit signal, that means when we have a 3 bits, this is 3 bits, and each of them could be 0 or 1, meaning that we have to the power of 3 different code, 8 code. Okay, now, if the analog signals, for example, varies between 0 to 5 volt, we would have 8 different code from 000 to 111, okay? And we could divide this variation into those codes. Like if it's 1 volt, it means a certain code. And the ADC would translate that value based on the transfer function, and it coded based on that, for example, 3-bit digital code. Okay, now these in this transfer, precision matters because any offset or drift or gain error, okay, basically affects the ADC's output, meaning we have a problem in temperature control systems. We might have a problem in medical system or calibration equipment or industrial process control. So having a good ADC performance, when we're talking about low varying or constant voltages, like DC testing, okay, it's very important. We call that DC testing, as a static testing. We are going to go deeper to talk about what is static testing, but just to introduce, static testing is regarding the testing of the ADC with a DC signal or a slowly varying signal, and we are gonna like basically see how the ADC would behave if the input is such a slow or constant voltage. Uh, so this is kind of like what we care about and the critical role of ADCs in system measuring and testing. Now, without these ADCs, none of the control system or modern system would work. We wouldn't have a processing, we wouldn't have a feedback control. The subsystem cannot communicate intelligently with each other. But why we don't do that using the same analog signal that we directly get from our sensors, and we have to do kind of like change that or convert it to a digital signal. Now, analog signal or time varying signal are very vulnerable when we talk about the noises or like harmonic distortions. Okay, so by converting them to the digital signal, okay, we basically mitigate or reduce those distortion or effect, like environmental effect or interference that happening to the signal. So we make the information better for processing purposes. Now, if we need analog signal later on, we could again convert that digital signal using DAC, digital to analog converter, to analog signal. For example, when you wanted to like display what you measured in an oscilloscope, the measurement would go through the digital ADC, become digital. Inside the oscilloscope, it processes the signal, the digital signal, and when you wanted to like show it in the screen in the oscilloscope, you need to again transfer it from digital to analog so you could show it in the screen. Okay, so this is kind of like the gist of why ADC has a critical role and why we have to make sure that we have a precise behavior. Why we need precision. Okay, we know ADC has a critical role, but why we have to talk about the precision. Now, in the basically ADCs, okay, we have to pay attention that normally ADCs has a variety of architecture. Okay, we have different type of analog to digital converters. For example, it could be successive approximation, which we know it as a SAR architecture, or it could be sigma delta, pipeline, flash, dual slope. All these architecture, they behave significantly different. Each of them has a unique sensitivity. Okay, so some of these architecture may be very sensitive to the temperature of the environment, or some of them would be very sensitive, have a very high sensitivity to the noise in the input signal. And based on their capability and the architecture, there are different application that each architecture is most kind of like compatible with that application and is the best architecture to use on that application. For example, when we talk about the SAR, because of the high speed and moderate resolution that it provides, is a very good ADC architecture for like a power monitoring or kind of like or any kind of like type of measurement of the physical quantity, or in other kind of like aspect, the other categories or other types has different application. We are going to talk about that briefly and see what are the differences. Now, why IEEE 1057 standard exists? Now, we know that ADC are critical. We know we have to make sure that we have a precision on the ADC, but okay, why we have to use IEEE 1057? Now, before IEEE 1057, okay, each vendor, each manufacturer would test or validate their ADCs based on their own test procedures, based on their own assumptions. So you can imagine that how that would be problematic because there wouldn't be a universal system to define the quality of the ADC. So the users cannot rely on the validation done by vendors. And some of the vendors would actually deviate or implement some assumption into the procedure of testing that would favors their kind of like product. So it would have the result would be a misleading specification. Okay, so IEEE 1057 kicks in to have a for us to have a universal definition and procedure for testing all those architecture. But we have to notice that different architecture behave differently when we talk about the evaluation of the performance. That IEEE 1057 basically, first of all, define a standard test method. It define critical definition parameters. So avoid if we could avoid the vendors or manufacturer exaggeration in the specification. And another way, in another part, it provide us a guidance for calibrating the instrument and the procedure. So we make sure that, for example, we have zero drift, we are accuracy, and we know the errors that we introduce to the test. Okay, because no matter what, we cannot have an instrument that has zero error. Calibration would increase or enhance that situation, but it never mitigate fully. So we have to know, based on one of the results of calibration is the uncertainty of measurement. Okay, so we have to know what type of error we are introducing to the testing process, so we could distinguish it from the errors in the performance of the ADCs. Okay, so this is kind of like the this standard. Now, each type of we said that each type of architecture has their own behavior and they have their own unique sensitivity. So when we wanted to like test those, okay, we have to go beyond the ADC's types. Okay, so we have to consider reference voltages, okay, or input signal purity or clock accuracy. So and environmental factor, because the environmental factor actually affects significantly on the performance of the ADC. The parameters that is defined as a criteria, or like we could say, the measures that we could, based on them, define how efficient or how accurate those converter are defined in IEEE 1057. There are several different parameters, like you can see some of the example: INL, DNL, SI, NAD, THD. We are going to slightly talk about those parameters when we talk about when we're gonna review a case study of how we test a specific instrument. But the exact definition of each of these parameters, okay, exists in a standard. I believe it's a section 3 when there are its title definition when you look up each of these parameters and have the precise official definition of these parameters. Okay, now let's talk about basically the history and the motivation behind introducing the IEEE 1057. Before this standard, we said vendors made unverified performance claims. There were no reproducibility. There were inconsistent test conditions, dangerous assumption during their testing that would favor their architecture. So this IEEE basically brought a legal engineering alignment. It's very important. This is a legal engineering alignment, so it could protect buyers, developers, and even regulators. Okay, so if you meet the specification of this standard, you can make sure that you already meet the responsibility that you have as an engineer to design analog to digital converter. Okay, and you are good because this standard is a universal standard, and it's basically if you pass this criteria, it means you pass all the regulations international. Okay, now why it's matter to consider that? One is legal protection. We said that, okay, this standard is a baseline. So it's the minimum quality, minimum accuracy that you have to have, okay, for your design and the product that you are developing, okay? Not only that, when you test your ADC using this standard, the result should be documented in a specific way with a specific terminology. So everyone have the same language, everyone have the same framework, same structure, and everyone could understand what you did and what were the result of your process, testing process. As we said, is an internationally recognized standard, so it is basically the backbone of verification, compliance verification and evaluation for these type of standards. And since it has it's become a common language in this specific area, basically all the engineers, regulators, and suppliers use these standards to define their product for engineering purposes. Now, the technical diversity of the ADC's architecture, okay, basically demands a uniform evaluation. So we cannot have different type of evaluation procedure for different architecture of the ADC. So we have to go beyond the architecture. Okay, so those difference between the architecture create a range of operational behavior. Some of the ADCs are optimized for high speed applications, okay, where sampling rate and signal to noise ratio is critical. Others, like sigma delta, okay, are mostly focused on the resolution and noise shaping, which makes them very suitable for low frequency but high accuracy system. Okay, or in power system, when we wanted to like have a very good linearity, we want to have an offset accuracy and a temperature stability, then SAR is the best architecture for our kind of like for this type of application. Now, This diversity shows that no single metrics or test setup can fully capture the performance of all ADCs. Okay, so what we have to do is that we have to create a framework beyond the ADC architecture so we could test all of them in one standard procedures. Okay. The IEEE 1057 defines two category of testing. Okay, in the testing system, in the test that it defines within the standards. One is static testing, another one is dynamic testing. Again, we are gonna go through that in details. What are they and what are the parameters are for each of those categories, and we're gonna discuss that. But this approach that the standards develop gives us a uniform evaluation process. So we could meet all the parameters that are important, but for each specific architecture or application, we might have to emphasize like parameter number 1, 3, 5, and parameter number 2 is not important for us. So when we testing, we focus on those parameters. Okay, but the overall process is universal. Now, let's talk about the different architecture to have a little bit of sense of what we mean when we say different architecture has different characteristics. As you can see in the table, like for example, the SAR has a resolution, is a moderate resolution, 10 to 16 bits, okay? But the speed is quite high. Okay, we could go to the tens of mega sample per second. So that, and you can know that you can understand that when your resolution increase is a trade-off, your speed gonna reduce and vice versa. Okay, so resolution and speed go against each other. So we have to have a trade-off based on the application. So these moderate resolution and high speed, relatively high speed, makes them very good for industrial sensors. On the other hand, sigma delta has a higher resolution. You can see that it's 16 to 24 bits. So when the resolution is high, you can see that the speed are lower than the SAR. So it ranges from kilohertz to a low megahertz kind of like values. So that makes them, because of the resolution, make them perfect for audio recording. Okay, or like flash has a relatively lower resolution, but significantly higher speed, up to like 4 gigasample per second. Okay, that make them a very good architecture for when we talking about the high speed oscilloscopes or radio frequency, when we have a very high frequency change in our input signal. Okay, and you could go through the other examples. Is basically I wanted to show how the characteristics of each architecture make them suitable for different applications. Now, because the IEEE should support a broad range of ADCs, basically the standard should not limit itself to a specific industry or application. So that means that this standard provides actually flexibility needed to test ADC, okay, for performance classes, sampling rates, resolution levels, all those parameters, okay? Because of that, the IEEE 1057 is intentionally modular in a structure. Okay, the key section are terminology and definition, static testing, dynamic testing, timing testing, and calibration methods. You can go through the standards, and these are the sections that you will see in that specific standards. Okay, so this modularity would actually gives you the opportunity or the flexibility to select and apply what is the relevant part of the standard to your specific case. Now, IEEE is also a living standard, so it evolves continuously. So if like based on the industrial experience or based on the enhancement of the technology, okay, the IEEE would continuously change and improve, okay, improve. So when you want to like use that, you need to make sure that you are using the right version of the IEEE 1057 for your technology. Okay, so if you're using the high edge technology, the last level of technology, you need to use the last revision of the IEEE 1057. Now, when we talk about sorry, when we talk about testing an ADC, is not just applying a signal and reading the output. There are several critical dimensions that we have to carefully note when we are talking about testing ADCs. You can see the 4 dimensions that are defined in IEEE 1057 in the slide. Each dimension actually impact the measurement accuracy, repeatability, and relevance, especially when we're comparing different architecture with each other. Okay, the first dimension is the type of signal. So we have to make sure to distinguish what kind of signal we're using as an input. Is it a DC ramp? Is it a DC step? Is it sinusoidal? It's like a two-tone or impulse response. What kind of input signal we are introducing to the ADC to test that? Okay. For example, DC ramp and DC steps are normally used for static testing. Okay. And we are going to talk about the different parameters that are defined within the static testing and how they would show the quality of our ADC and the performance of our ADC. The second dimension is the sampling mode. The sampling mode is defined as how the ADC samples the input signals. Okay, there is different configuration. It could be internally clocked. It could be externally clocked. It could be synchronous or asynchronous. What those mean? Internally clocked, that means the ASD uses its own sampling clock, which limits the control over the sampling, but is very easy to implement. The externally clocked ADC are more precise because we have control over the sampling clock, okay? But it's harder to implement. It's more complicated system. Now, what is the synchronous and asynchronous? If the clock and inputs are phased and frequency locked, so they don't change, so our clock and the input reference are basically locked together from the phase perspective and frequency perspective, we have a synchronous clocking. And you can kind of like guess that what asynchronous means when when the clock and the input signal are not locked to each other. That would be the asynchronous kind of like situation. And I believe if you are familiar with the ADC and the analog signal, you can sense how these sampling modes make a difference in our output result. Now, the third dimension is the measurement interface, okay, which basically is how the output of the ADC is accessed and processing happens during the test. Okay, so some ADC provide the digital data output, like with the interface like SPI or LVDS or parallel buses, which directly capture the output through the data acquisition tools. Some of them, some of the other setups needs a DAC. Okay, we need to convert again the digital to analog signal so we could use the measurement in our instrument. The fourth dimension is the environmental control. So it means how well the external test conditions are managed. So we said that the temperature stability is one of the examples. The power supply regulation is another one. The electromagnetic interference is the next one. Okay, so we have to make sure that we are controlling and managing these external conditions which significantly affect our result. For example, if the temperature changes plus or minus 1 to 2 degrees Celsius, it would introduce an offset drift. Okay, because it's changed the characteristics of the circuit. Okay, or noisy power supply introduce an inaccurate or an extra distortion in the output, make the ADC deviate more from a linear performance to a more distorted nonlinear performance. So, and EMI is also like I think one of the obvious ones. So if we have electromagnetic interference, therefore the result would be polluted with externally injected noises. Now that we kind of like define the general testing procedure, let's talk about what we kind of like mentioned, the words that we mentioned as static parameters, static testing, and dynamic testing. Now, these standards define several static testing. But what is static testing? Static testing shows how accurate the converter responds to the slowly changing input. Okay, so basically, this is essential for understanding the transfer function of ADC, how it would transfer the analog signal and code it to a digital codes. Okay, one of the parameters that the IEEE 1057 introduced for static testing is offset error. This offset error is actually the difference between the actual transfer function, okay, and the ideal transfer function. Let me show with a graph. Like, for example, we have a 3-bit system. So we have 8 levels from 0, 0, 0, which is here, to 1, 1, 1. And let's say we have a variety of a voltage from 0 to 1. The ideal case is a line that converts this analog signal to these digital codes. The line means we have infinite number of the bits. So each individual point in this 0 to 1 volt variation would create its own digital code and its infinite number of the codes, but it's not possible. So we have a limited number of codes. For this example is 3 bits, so we have 8 one. So what happens is that we will have some steps, that each level of steps translate the certain specific interval of the voltage variation to a one code. Like, for example, if it's, and we have 8, so we have to like divide them equally. So it's 1/8 of the 1, which I think is like 0.12 volt. If we have 1 volt, 1 divided by 8 is like 0.12 volt. So if the voltage is from 0 to that 0.12 volt approximately. We are in the first step, and the ADC translate this level of variety to the code 000. Now, if the variation, the voltage goes higher than 1/8, but lower than the 2/8 of the final value, which basically, by the way, we call this as a reference voltage. If it goes between 1/8 and 2/8, it creates another step, meaning it would translate this interval to 001. And it continues like that. Now, offset error is when these steps are shifted up or down. So you can imagine if we shift up, that means, let me use another color. Where is that? If we shift up this value, okay, you can see now the interval between 1/8 and 2/8 has a different translation in the code. So if we have an offset, it means the converter would miss one of the codes, or it would translate the variation into the wrong code. So it could be plus offset, goes up, or goes down minus offset. Now, another difference is the gain error. The gain error is the slope of change. This is the ideal line. Now, if our slopes deviate from this, so it goes faster, the step goes faster or steeper, again, you can see that it would make the transfer function to wrongly translate the certain interval to a digital code. So we are going to measure that slope to see if the gain error exists or not. Now, it could be, again, positive or negative. Now, we have another factor that is named as DNL, or differential nonlinearity. Now, what that means? DNL measures the deviation of each step, okay, from the ideal step. So we said we are going to divide them equally, but that's in a ideal world. In real world, these width of these steps could be different. So one is smaller than the next one. Now, the ideal system, when we ideally divide the variation interval of the voltage, the global variation, into, like, for this is example 8 division or n division, we call each of these equal width as LSB, or least significant bit. So ideally, this interval is called LSB. Now, if one of the steps based on some sort of error is less than LSB, then we have a differential nonlinearity. It could be higher than LSB. So again, DNL could be positive or negative. Now you can imagine if this difference exceeds 1 LSB, that means we are missing one step. Imagine this step increases more than 1. That means we eliminated this step. So we are missing this code. Okay, now this is the kind of like the consequence of DNL and the meaning of the DNL. Now we have another factor that we use in static testing that is named integral nonlinearity, or INL. Now, what that means? That integral nonlinearity, or INL, is a deviation of ADC's actual transfer function from the ideal. Now, let's show it in a more clean system. So this is the ideal. Let's say this, come on. This is the non-ideal. Okay. Now, if we use a regression to create a, come on, a transfer function for the actual steps, you can see these differences between the transfer function and that ideal line, okay, would create an error. We call these differences as an INL. Okay, is that clear for everyone? If there is any question, please ask. Okay, so you have to pay attention. You see, the INL defines by the transfer function. Transfer function happens by a regression over the actual transfer function of the ADC. Meaning INL is a global parameter. It needs all the information to be measured. But DNL focuses on one step. So DNL is a local parameter. So you need to make sure you understand the differences between these two parameters. Now, beside the static testing, we have dynamic parameters in a dynamic testing for ADC. Now, what is the dynamic parameters? In dynamic parameters, we measure how well that ADC performs when we have a rapidly changing input. It could be a sine wave, it could be a modulated input, okay, or any type of high frequency change, like RF, as an input. Now, these type of parameters in dynamic testing are normally focused on frequency domain behavior. So one of the base tools that we use in dynamic parameters is FFT, fast Fourier transform. For measuring all of these parameters, we need to first conduct an FFT analysis over our output. So we know the harmonic in our output. Now we could quantify it and calculate these parameters. Now, one example is signal to noise ratio, which is one of the famous ones. Okay. What is it? The SNR. SNR is a ratio of the power of the fundamental input signal, what you want to see, okay, in ideal case, to the power of all non-harmonic noises. Pay attention. Non-harmonic noises. Harmonics are not defined in SNR. Non-harmonic noises are defined in SNR. Now, how we calculate the harmonic, another parameter kicks in, named THD, or total harmonic distortion, where this is show how much harmonic content appears in the output. Okay, now there are other parameters like SFDR, which is the ratio of the power of the fundamental signal to the power of the largest spurious frequency component. It happens when you have a harmonic distortion or clock fit-through or crosstalk between the systems. So basically, it shows that how well ADCs has the ability to resolve weak signals in a presence of a strong tones, and it's basically critical for radar or wireless system or spectrum analysis. Another one is SINAD, which is a signal to noise and distortion ratio. Now, based on the name, you could see that this is basically a combination of the SNR and THD. This parameter includes both noise and harmonic distortions. So it gives us a more comprehensive picture rather than the SNR itself. Okay, so this is like the parameters that are another parameters also like effective number of the bits. These are basically the parameters that we use in a dynamic testing to capture the behavior of the ADC when we have a high frequency change or high speed change in our output. Now, there are several aspects that we need to like pay attention when we talk about the dynamic testing that could affect our result. One is what type of input that we have. Is it a coherent sine wave? Okay, which means the signal has a frequency that is an exact multiple of the sampling frequency, okay, divided by the number of samples. So it's coherent with our architecture, okay, or it's not. Then it would be different. So it's if you have to pay attention to that, you can see how the sampling frequency and the frequency of the input signal could affect the situation. For example, because we have to be able to like reproduce the analog from the digital codes. So if we have this type of frequency as an input sinusoidal, if we follow the sampling space, meaning we have to have at least twice the frequency of the sine as a sampling space, then we would have at least 2 points for each cycle. Now we can reproduce the analog. But if we don't have a coherent sine wave as an input with a sampling frequency, that means, for example, we have this, but our sampling is non-coherent. Okay, so you can see that this sampling, if we wanted to like reproduce the analog signal, it would mislead us to another type of analog signal. Now that we kind of like defined static parameters and dynamic parameters, we have to talk about, okay, what are the differences? What are the comparison of the static versus dynamic testing? Okay. We already know that the whole categories, the whole testing procedure of ADC is categorized to two, static and dynamic testing. Okay. Each method evaluate different performance aspect. Okay. In a static testing, we said it examines the ADC behavior when we have a steady or very slowly changing input. On the other hand, in a dynamic, we have a high speed change in our input. Okay. Normally, the static test includes the DC ramped or DC steps or low frequency waveform as the input signal, and the type of the testing normally this static testing normally focuses on the accuracy and the linearity of the transfer function of our ADCs. Okay, we already said there are several parameters: offset error, gain error, DNL, INL. These parameters show how accurate the transfer function is and how linear it behaves. Okay, so when we, like, for example, talk about the SAR architecture or dual slope, this static testing is particularly meaningful. Okay, because it shows the precision when we use a slow speed applications. Now, What about the dynamic testing? Dynamic testing is the evaluation under a rapidly changing input. Okay, it could be a coherent sine wave, it could be two-tone signal, a modulated waveform, any kind of like type of rapidly changing. These type of tests focuses on the noise, distortion, and frequency domain integrity. Okay, we already talked about some of the parameters like SNR and THD, or or SINAD, and a little bit discuss what they represent. But we have to pay attention that the dynamic testing is heavily rely on a Fourier transform. So your FFT and the window that you use for the FFT is very important for you to measure those parameters. Now let's talk about the designing a test through IEEE 1057. Now, when we wanted to like define the test, the first step is to know what device is under test. Device under test, or DUT specification, is very important. The performance parameters of that DUT is very important in how you define the test for the specific case that you have. Okay. After that, when you define precisely what you are testing, you create a block diagram to show the flow of testing, the procedure of the testing. Where to start, where to end. What is the configuration? Then we have to configure the signal source. Now, I want to test this specific device. I want to go through this process. Now, when I wanted to like what I wanted to know about this specific ADC is 1, 2, 3, 4 characteristics. So what type of input could give me what I want, the evaluation that I want. And after that, you develop your test plan. Now, the static testing include applying like a ramp signal. We normally use a DAC to create a slowly changing ramp signal. We record the output. We construct the code histogram, that graph that I showed you. Okay, and analyzing the distribution of the code across the input range. The transfer function that I showed you, the step transfer function. And then we compute the performance metric. We said like, okay, there is an offset error, there is a gain error, DNL, INL, and we're checking the performance against these parameters. Now, how to calculate them is has a precise equation which is defined in the standards of like, okay, when you measure this transfer function, how you could calculate exactly the offset gain error, or like the offset and the gain error, or DNL and INL. For dynamic testing, the procedure is you apply a dynamic input, could be like a coherent sine wave. Normally is a coherent sine wave. Okay, you capture the output, you run an FFT, okay, and then you calculate the parameters that you want based on the FFT of the output of the ADC. Again, the equation for calculating these specific like SNR, THD, all the parameters are mentioned in the standards precisely. You need to follow those specific equations, because like for example, THD has different type of equation based on what you need. You might want to define the THD as in a decibel unit or as a percentage or as a per unit. Okay, the equation would be different equation. So in this standard, we use the decibel one. Now let's talk about a specific case study. As we said, the first step is to understand what we are testing. Okay, so we have to understand what is the device under test. In this specific case study, we are going to test a specific ADC made by Texas Instrument, and the model is ADS 7042. Okay, it's a 12-bit SAR ADC, so we know what it is, we know the resolution. Okay, and it normally operates at a medium speed, and it's commonly used in industrial sensing and monitoring application. So now we know what is the device, what is the application, what are the characteristics. Now we move forward to set up the test. Now, how we to set up the test? We need to, based on the IEEE 57, set up the test equipment. We need a signal generator to create the input, okay, based on what we want to measure for SAR ADC. We need a unity gain buffer, which makes sure that the signal source can drive the ADC input cleanly. Okay, we need an anti-aliasing filter to remove the high frequency noise from the input. We enter the input, this is the set setup. We enter the input to the ADC that we are going to testing. So signal generator, gain buffer, anti-aliasing, and then the clear, pure input is going to be injected to the ADC as an input. After that, we capture the data from the output of the ADC. It could be read a digital code, and we could store and analyze it, and verifies, and we use an oscilloscope to verify the signal going into the ADC is clean. So this is our test setup. Now, as we said, we have to make sure that the environmental conditions is also under the control. So one aspect is the temperature. So not only, but pay attention, not only we have to control the temperature of the room, we already know any type of electrical or electronic circuit, when it runs, it heats up because it has a power loss in it. So not only the temperature of the room, the testing environment is important, we need to make sure the temperature of the circuit is already stabilized. So the variation doesn't exist in the temperature in any kind of like way. So how to do that? We need to let the system work for like 30 minutes or an hour. Some system needs more to make sure that the temperature is stabilized. The definition of the stabilized temperature is when the temperature rises less than 1 degree Celsius within 1 hour. If we reach that slow rate of change in the temperature, then we can say, okay, our temperature is stabilized. We can run the test now. So this is one aspect. Another aspect is the EMI interference for environmental condition. We don't want to introduce noise or error from external devices. Like you might have your cell phone in your pocket when you are testing that. Certainly, it would create some electromagnetic interference in the testing. So you need to have a metal shield, okay, to shield the EMI, external electromagnetic interference, to your system. And you need to verify that your voltage reference is accurate, and you have to use a very high precision multimeter. Okay. So now that we have the condition set up, we know what equipment that we wanted to use for the test setup for this specific case study. Now we have to show what type of test we want to perform on that SAR. We already said there are two categories, static test and dynamic test. Okay, so in that SAR, a specific SAR, because of the application and because of the characteristics, we need to do both static test and dynamic test. But we chose the parameter based on our own application. Okay, as you can see in a static test, we chose these four parameters, and in dynamic test, we chose these two parameters. Now, in a static test, we are applying a slowly increasing voltage. For example, like in this case, we introduced a 0 to 3.3 volt based on the architecture and the specification of that SAR, the specific model of SAR that we're using. And we record the digital output. Now, when we test the INL on that on the histograph of the output of this ADC, specific ADC, we saw that the measure of the INL, we calculated the measure of INL is 1.8 LSP. Okay, what described by the standard as a criteria of pass and fail is that the INL should be limited to 2 LSP. So we are 1.8, we are good to go. We passed this requirement. We calculated the NL based on our measurement. Remember, the INL is global, DNL is local. And the highest DNL that we had, okay, is 0.95 LSP. We already talked about that. In order to do not miss any a step or any code, we need to have a DNL in the range of plus minus 1 LSP. We have the highest value that we had is 0.95. So again, we pass this requirement. We calculate the offset error based on the histogram that we have. And it shows basically how shifted up or down that transfer function is based on from the ideal situation. And what we measured is that we have 0.6 LSP shift in our transfer function. It's a positive, so it's shift up. Okay. And the standard defines a limit of 1 LSP as a passing criteria, so we don't miss any of the steps, any of the codes. Okay. And since we are lower than the limit within the range, we again pass the offset error for this specific ADC. We test the gain error, which is how what is the slope of that transfer function. The actual transfer function differs from the ideal transfer functions. We calculate that it's 1.1 LSP, okay, meaning it's a little bit has a higher slope, higher value as a slope. Is positive, sorry, higher value is more than 1. So it's higher value of the regarding the linear one. And the definition, the passing criteria for this gain error in the IEEE 1057 is 2 LSB. So since we are in the correct range, it means that our specific ADC is passing these parameters too. Now, what that means? That means this converter reproduces analog voltage as a digital value perfectly. Not perfectly, faithfully, reliably. You could rely on that. It does not skip any codes. Okay. It has a clean relatively good linear transfer function, and it's well behaved. Okay. Now, what about the dynamic testing? For dynamic testing, we said we need to like provide or like apply a pure sine wave or a coherent sine wave into the input. And then we run an FFT on the output and we measure the parameters that we need to pay attention to or focus on, and that are important for us. In this case, for the application that we have, the ENOB, which is the effective number of bits, is one of the parameters that we wanted to like assess for this specific case. What it shows the real world resolution of our ADC. We have a resolution. We said, okay, it's 12 bit, okay, but what is actually the resolution of that ADC in real world condition? We measure that, and the measurement shows that it's 11 bits. So first and foremost, it has a slight deviation from the specification of the manufacturer. Manufacturer claims it's 12 bits, but the real world measurement shows it's 11 bits. Typically, this type of ADC shows 11.3 bits. So it shows that a specific model that we test has a slightly lower resolution than even like an average typical SAR ADC. Okay, so this is one of the kind of like a shortcoming for this specific test that we run. Now, pay attention. This is not representing the whole model, the whole production line of this specific model in Texas Instrument. The specific ADC that we run a test on, the model and the serial numbers is very specific. Okay, that specific one has this result. So if you test another ADS 7042, you might see different values. Okay, now another one is SFDR, the parameter that we are measuring. It shows the distance between the main tone and the worst spur. The range that is acceptable in a standard is it should be higher than 80 decibel. Now, what we measured for this specific case study is 85.1. So it's higher than the limit. It has an excellent kind of like SFDR. Now, the only problem that we see is that the ENOB is slightly lower than the speed limit. But what would be the cause of that? Okay, it's not just the problem with the ADC. One problem could be electromagnetic interference. We have to make sure to eliminate the electromagnetic interference fully and mitigate that as much as we can. So we make sure that in the lab, we don't introduce any error, then rerun the error and see how that would affect the value. Would it enhance it or not? Or we could have a USB noise or switching power supply noise or unshielded laptop when we want to like do the FFT analysis. So all these could be important. And after we address this issue, it could help us to improve the prompt. Now, we define the process, we talk about the testing, and we go over a case study, but there are some challenges in real world that we cannot mitigate, but we have to control it, okay, and understand it. One is the temperature stability. We already talked about that. It could deviate the result. So we need to make sure that we control the temperature variation. Normally, they use kind of like a uh, temperature cabinet, which is a stabilized environment in regarding the temperature for the testing. Another aspect, oh sorry, it's a wrong slide. Another aspect is a grounding issue. Most of the testing facility use one ground for all the equipment. So the laptop, the ADC, the signal generator, all of them uses one ground, the plug-in ground. Okay, that could create, because they are local, that could create a ground loop. So if there is a current injected to the ground, for example, from the signal generator, it could go also not only to the ground, but a portion of that would go, like, for example, to deviate the input of the laptop or the oscilloscope. So we need to avoid that kind of like a problem with grounding issue to make sure all the equipment are this kind of like specifically connected to the point of the ground and there is no loop between them. Okay. And after that is a software limitation, how correct our FFT are. Okay. So we could use a rectangular window to calculate the FFT. Okay. And it's basically one of the window function that creates a spectral leakage. So an error in the FFT. Or we can use a more sophisticated window like Blackman-Harris window, which helps to have a better side lobe suppression. So these are the different challenges that we may face in the testing the ADC. Now, 1057 is not a standalone kind of like one soldier kind of like army case. There is an ecosystem of a standard that complement the 1057, and you need to make sure that you follow those complementary standards based on your application. Like IEEE 1241 is the expanded ADC testing. 1139 covers signal generation. 1159 covers the power quality. 1451 try to cover the smart sensors. So these are complementary. All these like signal generation, smart sensor, all these like power sources, they are within the structure of test procedure in IEEE 1057. But these complementary standards make sure that you meet all the requirements that you need to pay attention to. Okay, thank you very much. If you have any question, please let me know. Otherwise, this is the end of our discussion. Any question? No? Thank you and have a good rest of the day.